Okay, I'm sorry. You guys are right. I had not resumed recording. Okay. Unfortunately, we don't have the first few problems here on recording, but sorry about that, guys. I think we're in sync now. Um, I typically always leave the recording on and get about 10 or 12 minutes before the session starts. And some of you that have gone back to the recording uh, have waited and waited, or you can fast forward right to the beginning of the lecture. Okay, let me just check. Okay. All right, good. All right. Okay, guys, I think we're all set now. Sorry. All right, so in this problem in number 4, we can, let's see, I'm sorry, number 3. Okay. And here we can go into StatCrunch and calculate the 95% confidence interval. All right. And so let's go ahead and do that. Okay, so here we'll go to our CStats, and this is a one sample problem, isn't it? Okay, and we have the summary data here. I'm sorry, I selected the wrong option here. Let's select proportions. This is the proportion of cell phone users, okay? So that's a summary. And the sample data are 139 over the number of observations, which is 420,040. Okay, and we want the 95% confidence interval. Let's go back and double check that. Yes, the 95%. Okay, and now we compute, and this gives us our results here. All right, and the lower limit here you see displayed in StatCrunch with the upper limit. Okay, and we'll round that to 3 places. So the rounding is to 3 decimal places, and you can see from your result there that when we round the lower limit, we'll get 0.00028, and the upper limit rounded would be 0.0039. Okay, so these are the correct answers here. All right. And then in part B, do cell phone users appear to have a rate of cancer of the brain or nervous system that is different from the rate of such cancer among those not using cell phones? Why or why not? Okay. Well, the interval does not cover the value 0.0416%. Now remember, we converted our results in StatCrunch to percent, didn't we? Okay, so this, let's say, prior value of 0.0416% does not appear in our confidence interval that we've just constructed here based on the sample data. Okay, so we can answer yes to the question that the sample values give us a different rate of cancer, right? Okay, any questions about this problem here? Number 3. We good? Okay, let's move on. Okay, and in this one, notice that the student missed part of this problem, okay? In a test of the effectiveness of garlic for lowering cholesterol, 49 subjects were treated with garlic in a processed tablet form. So now we're going to look at cholesterol levels before and after the treatment, the changes before minus after in their levels of LDL, which is the low cholesterol. That's the more harmful cholesterol. Does this mean has a standard, has this garlic effectiveness is measured? Okay, and the changes in the LDL have a mean of 2.8 and a standard deviation of 19.4 based on the sample of the 49 subjects. Okay, so we would like to construct the 95% confidence interval estimate of the net change, of the mean net change in LDL after the garlic treatment. Okay, so let's go into StatCrunch now and notice that these values were incorrect here. Okay, all right. Okay, so the correct answers are given here, and let's now go up to our StatCrunch, and we'll now specify the sample values here. So for our Z-stats, we've got a one sample. Again, now we've reduced our data to one sample here, and we're given a summary. And so the sample mean for this problem is 2.8. The standard deviation here is given to be 19.4. And the sample size is 49, okay? And we're going to calculate the 95% confidence interval here, right? Okay. All right, and here we have the two limits here of negative 0.63 and 8.23. Okay. All right. Now, let's see. We used the Z, didn't we, just now? And so these values here that the student input were the Z values. Okay. Now, the correction is probably because the T distribution was used with 48 degrees of freedom. So let's go back in and check that. Okay, so we'll go back into stat.
Sorry,
question?
Someone is in the waiting room.
Oh. Okay. All right. So let's go back into the program. Thank you for reminding me. Okay, so let's go back to StatCrunch. And now, instead of the Z statistic, let's see what we get with the T-stat, okay? So again, we've got a summary. We'll give it the same sample values here, 2.8. Sample standard deviation of 19.4. And we have the 95% confidence interval, okay? The sample size is 49. And now we compute the T interval, and here are the values we get, negative 2.77 and 8.37, okay? Okay, and now the program likes those answers better, all right? And
I have a
yes.
question about how do you know when to use a z-stat versus a t-stat?
Typically the t-stat, and this is what I was going to tell you, in this problem, we're not given the population standard deviation. Regardless of the sample size, if you use your estimate S in your confidence interval, then the t distribution is probably more appropriate. Okay, so all you have to remember is z when the population standard deviation is given. Otherwise, you can use t. Okay, now our textbook indicates that when the sample size is larger than 30, then you can reasonably use the z distribution as well. So both of these answers are correct in the sense that I've used the z, we've used the z to get the negative 2.63. If you use the z, you get negative 2.77. Do you see that?
Yeah, but so like on the test, like it's not going to take both answers. So just kind of confused.
Well, I think to be conservative, the textbook indicates that when you don't have the population standard deviation sigma, and you only have S, which is based on the sample, regardless of the sample size, use the t distribution. Does that work for you?
Yeah.
Okay, so you have a protocol. If you're not given the population standard deviation sigma, fall back on the t and you won't go wrong. That's the lesson here from this problem. Okay, all right, now the next question says, what does the confidence interval suggest about the effectiveness of the treatment? Okay, all right, so notice that the confidence interval does contain 0, doesn't it? Okay, so if it contains 0, then it probably is suggesting that the before minus after, if 0 is contained in this interval, then the garlic treatment probably has no effect. All right, you see that? So we'll answer A here. The confidence interval limits contain 0, don't they? Okay, notice that the lower limit is negative, the upper limit is positive. So 0 is one of the potential values of this mean difference here, mu, indicating that it probably doesn't give us a 0, and 0 would indicate that the treatment is really neutral. There's no really positive treatment effect there. Okay. All right. Next problem. And here we have salaries of 33 college graduates who took a statistics course in college with a mean of $61,000. And again, we're going to use sigma. So when you see sigma there, then that's the signal that you should use the z distribution. And we'll construct a 95% confidence interval. Sigma, the population standard deviation, is 11,340. Okay. Now the z would be justified, but for this test, we'll use the t distribution. So let's go into StatCrunch. Okay. And we'll use a t distribution for this problem. We have a one sample with summary. Okay. And in this problem, 5, our mean salary is 61,000. And now the, wait, I'm sorry. I have a t here, don't I? But since sigma is known, we can use the Z. So let's go back, choose Z, one sample with summary. Okay, are we all on the same page here? Are we good? Okay, so now I'm in a Z regime because the standard deviation sigma is known. The sample mean is calculated to be 61,000 here. Standard deviation sigma is given to be 11,340. The sample size is 33, and we're going to calculate the 95% confidence interval. And here it is. Okay. And so we've got our two boundaries here, the lower limit and the upper limit. Let's go back to the review. Okay. And we'll round those values to the nearest integer. So in StatCrunch, it looks like we round up to the lower limit should be 57,131, and the upper limit should be 64,869. We've rounded up to the nearest whole number. Okay, and those are the correct values there. Okay, any questions about the confidence interval for the mean mu when the standard deviation is given to be sigma? Okay, all right. Okay, we can use the Z distribution there, not the T. Okay, and in this problem here, we're given the statement. Let's look at the statement of the problem here. A poll of 2,126 randomly selected adults showed that 90% of them own cell phones. Okay, so that's the sample data. The technology display results from a test of the claim that 91% of adults own cell phones. All right. So there's a claim that actually 91% of the adults own cell phones. Our data, our random sample shows 90%. Okay, is that value a significant value? Use the normal distribution as an approximation to the claim to the claim that P is actually 91%. Okay, and if we input these values into StatCrunch and calculate the 95% confidence interval, we would get the values here shown in the problem. Okay, if we did a test, and this would be a two-tailed test, we would get a Z value of -2.17 and a P value of 0.03. Okay, now notice the significance level given here for the hypothesis test for the population mean is 0.01. And just a spoiler alert, our 0.03 p-value is bigger than 0.01, isn't it? Okay, so that p-value is high enough that we would not reject the null hypothesis. That'll come into play down here. Okay, so the claim is not that the population proportion is less or greater than. Okay, so we can't use the one-tail test here. So all we're trying to do is check that it's 91 versus it's different than 91%. Okay, so it's a two-tail test. The test statistic is given to us up here and that's negative 2.17, all right? And the p-value is 0.030, okay? Now, there are some differences here, okay? And if you answered 0.030, okay, I would give you a correction on here. These values here, which are basically prediction intervals, I would not dock you if you answered 0.3, because that's what StatCrunch is going to give us up here, okay? So in checking your test, I can go through and check each of your answers, and if you got an incorrection based on your StatCrunch results, I would give you full credit, okay? All right, so 0.030 would be correct, all right, in my book. And in part D, what is the null hypothesis and what do you conclude about it? All right. The null hypothesis is always an equality here, isn't it? So from the test of the claim that 91%, that tells us that H naught is P is equal to 0.91, okay? And then choose the correct answer below, all right? And the correct answer here is that we do not reject, we fail to reject, because the p-value is greater than the significance level alpha. The p-value is 0.30, and it definitely is bigger than 0.01. So the correct answer is D, fail to reject the null hypothesis because the p-value of 0.03 is greater than the significance level 0.01. Okay? And then the final conclusion would be we fail to reject, so there's not sufficient evidence to warrant rejection of the claim that 91% of adults own a cell phone. Okay, so here you see a variety of correct and incorrect answers here. And you have to pull out the correct answer. And again, the caveat on this value here is that I would give you full credit if you answered 0.3 here, okay? All right. Any questions about number 6? Now, the problems that you did in your practice test had slightly different values, didn't they? But you're getting a lot of insight here into what the correct answers would be just by going through this particular version of the test, okay? All right. Okay, so let's go to the next one. Okay, and here we have, again, the wording of our problem. And let's read the problem. In a study of 420,122 cell phone users, 128 subjects developed cancer of the brain or nervous system. Test the claim based on a somewhat common belief that such cancers are affected by cell phone use. That is, test the claim that cell phone users develop cancer of the brain or nervous system at a rate that is different from the rate 0.0340% for people who do not use cell phones, okay? Because this issue has such great importance, use a very small significance level, okay? Remember, the significance level is the probability of rejecting the null hypothesis when it's true, okay? So we want that to be smaller than 0.05 or 0.01. So we'll use 0.001, okay? So we'll use a value of basically 1/1000, okay? We'll identify the null, the alternative, the test statistic, the p-value, and then we'll answer various questions about the claim, okay? So here is the correct hypothesis here in part D. Now, remember that we're not making any claims about the relation in the alternative. We're just saying that, is it different? Okay. So test the claim that it is different. So we'll use part D here. And the D option sets up the correct claim. P is equal to the common belief of 0.034% versus it's different. So part D is the correct answer there. And now the test statistic we can get from StatCrunch. So let's go into StatCrunch now. And now we're going to use a Z distribution here because of the large sample size, all right? And we know that the distribution of p hat here is a normal distribution because of the binomial theorem. Okay, so let's go into StatCrunch and go ahead and set up our proportion stats here. And we've got a one sample problem. We've got the summary data. So let's put in the number of successes here. In our problem here, the number of successes is going to be 128 out of a total sample size of 420,122. Okay, so we'll perform the hypothesis test here. And now we have to adjust our confidence level. And remember how we do that. We choose our confidence interval for P, and we set the correct confidence level here, or significance level. In this case, our significance level is 0.01, and 1 minus 0.001 is 0.999. So that conforms to a 0.001 significance level for the hypothesis test. Now, don't forget to go back and check your button here, and we'll type in our values here for the test. And the test is let's see, 0.0340%, which is 0.00034, right? And we use the inequality there as our alternative, okay? And now we're all set to go here. And we get our information here. And our Z-stat rounded to 3 places is negative 1.242, and the p-value is 0.2142. Okay. So here's our Z-value here. All right. Negative 1.24. We round to 2 places. And our p-value, let's see, we need to round to 4 places. And our p-value there is given to be 0.2142. Let's see, that's different from the correct answer. all right? And again, we're going to go by what StatCrunch tells us, okay? So that trumps any value. See, it's okay, 0.2136. All right, it's off by a little bit. Okay, and our conclusion here, since the p-value is higher than the significance level, we won't reject, we'll fail to reject, because the p-value is greater than the significance level alpha, okay? And the correct answer is that there is not sufficient evidence to support the claim, okay? Now the student had answered A, all right? There is not sufficient evidence to warrant rejection. Really what we're doing when we fail to reject is we're saying that the evidence in the sample is not sufficient to support the claim. Okay, that's really what we're saying there. Okay, so don't get mixed up between A and B, because really our focus is on the claim given in the test. And if we don't reject the null hypothesis, if we accept it in a sense, then that sample is not sufficient, it's not significant. So there is not sufficient evidence to support the claim, all right? And that's how we state our final conclusion, okay? And I was very careful in your worksheets to point out the difference in that language. When you fail to reject, it means that you have insufficient evidence to support the claim, okay? And the claim is your alternative. Our alternative here is that the rate is different from 0.0340%, all right? Okay, let's go to the next one here. In a large clinical trial, 391,140 children were randomly assigned to two groups, okay? The treatment group consisted of 197,256 children given a vaccine for a certain disease, and 31 of those children developed the disease. The other 193,884 children were given a placebo, and 106 of those children developed the disease. So on the face of it, it looks like the vaccine is working. Fewer children developed the disease when they were given the vaccine, okay? So what we'd like to do is consider the vaccine treatment group to be the first sample, and let's look at part A, okay? Now, at a 1.01 significance level here, let's test the claim that P1 is less than P2. Now remember, this is the alternative, okay? And now, is the hypothesis test better than the confidence interval? Generally, the hypothesis test is better. And it's better because we're using a fairly low significance value here, 0.01, okay? So this typically focuses in a better direction. So typically the hypothesis test is better, all right? Sometimes the interval, as we know, is a little more sensitive to the confidence level. So if we use the hypothesis test, we may actually get a more fine-tuned way to treat these results. So typically the hypothesis test is considered to be better for that reason, okay? Now, the p-value method and the critical value method are equivalent. You saw that from the solution sets in the worksheets there, right? And they always lead to the same conclusion, don't they? If the p-value is high, H naught will fly, okay? And the critical value method gives you a value on the z-axis, and it gives you the rejection regions, okay? And the rejection regions are the significance level, and a high p-value says that you're actually going to be inside the critical values, right? Okay, so all right, we'll base the test, of course, on the notion that the assumption that the two population proportions are equal, all right? And the other method actually just uses the estimated values of the population proportion, all right? Okay, now at the 0.01 significance level to be used to test the claim, what is the confidence level to be used? And here, remember, when we take the significance level, we're looking at z sub alpha over 2. So we have to split alpha, which is 0.01, into two pieces. And so we're going to put 0.01 level in both tails, and that'll give us the 98% confidence interval, okay? Because that'll put in the hypothesis test, we're looking at the left tail, P1 less than P2. We're putting a full 1% value in that left tail. So in a confidence interval, we should similarly put 1% in the lower limit and look at the level inside the confidence interval to be a full 2%, okay? Because it has to conform to both sides of the sample value p hat, okay? All right, so 98% is the correct answer there. And the confidence interval for the difference here, let's do that in StatCrunch, okay? And we'll get the values in StatCrunch there, okay? So we'll go up to, let's see here. This is number 8, okay? So let's go into StatCrunch and calculate our upper and lower limits given the data here. Okay, so we're going to use z-stats because we're involved with proportions in this problem. And we're going to use two samples here, right? And we have the summary data. Okay, so let's go ahead. I'm sorry. Oops, let me go to the proportions, not the z, but the proportions for two sample with summary. Everyone follow me? Are we good? Okay, let me check the chats here. No chats so far. No new chats. Okay, so let's for the treatment group, which is considered the first sample, here are the statistics. The number of successes is considered to be 31 out of the number of observations here, which is 197,256. Okay. And in the non-treatment group, in the placebo group, we have a total of 106 out of a sample size of 193,884. Okay. And our confidence interval here, let me just check that again. Okay. And we're using a 0.01 level of significance here. Okay. Okay. And so here we're going to use our significance level of 0.99. Let's see. We've got our significance level, and upstairs we're going to use 0.98. Okay. And here are our limits here. And if we, okay, so we have our values there. And again, we'll round these to 6 places as shown here. And you can see the interval for the difference is negative 0.00529 out to 0.00 negative 0.00250. Okay. And again, we've rounded. See the rounding here going off in the upper limit? All right. Okay. And you understand why we use the 98% confidence interval there. Okay, that's the correct confidence, 0.98. Okay. And again, we can state that because the confidence interval does not contain 0, right? Take a look at this confidence interval. Both the upper limit and the lower limit are negative. So it doesn't contain 0. So we would we would state that this confidence interval tells us that there is a significant difference between the two proportions. 0 is not in that interval, right? Some other negative value is. So that tells us that there is a significant difference between the two proportions. And because the confidence interval consists of only values less than 0, it appears that the first proportion is less than the second proportion. So there is sufficient evidence to support the claim that the rate, it never said polio up here in the statement of the problem, did it? But I guess it is talking about the polio vaccine. The polio vaccine was administered, it's still administered today, but it was discovered, I believe, in the late 50s or early 60s. So we would state that there is sufficient evidence to support the claim that the rate of polio is less for children given the vaccine than it is for children given the placebo. Okay? Any questions about this problem? Okay. Okay, number 9. Rhinoviruses typically cause common colds. In a test of the effectiveness of echinacea, 44 of the 51 subjects treated with echinacea developed rhinovirus infections. In a placebo group, 95 of the 108 subjects developed rhinovirus infections. Use a 0.01 significance level to test the claim that echinacea has an effect on rhinovirus infections. Okay, all right. Now, it's not saying that it prevents rhinovirus infections or that it causes rhinovirus infections. So what we have here is really a two-sided test. We're going to use inequality in the alternative because it's not asking us to show that echinacea improves or negatively affects the common cold, okay? Or the contraction of the common cold. So really we have a two-sided test here, don't we? So let's scan the various options here. Here's the one that we're going to use. Part E, because the null always contains equality. And in this particular claim, we're going to use inequality as our alternative, okay? And again, going into StatCrunch here, let's go back into StatCrunch and use the two sample proportions problem and calculate our confidence interval, okay? So let's go ahead and go to proportion stats, two sample with summary, and our treatment will be the first population here. So we'll type in our sample data from the first population. Okay. And let's see, here we've got 44 successes over a sample size of 51. And in the non-treatment, let's see, we've got 95 successes over 108. Okay, let's just double check that again. Yes, okay. All right. And now we're going to construct our confidence interval here at the 99%. Here we want alpha to be 0.01. Okay. So 1 minus alpha is 0.99. We'll change this to 0.99 here, since we're calculating the 99% confidence interval. And here are our results. Okay. Our lower limit is negative 0.165 if we round to 3 places. Our upper limit is 0.131. And let's read out the test statistic there. Okay. Oh, for the test statistic, let's see, we need the test. So let me set this up as a test now. Okay. And okay. So again, here's our test here. Our null hypothesis is that P1 minus P2 is 0. Okay, versus it's not equal to 0. Okay. And that's the test we have here now. And our significance level is 1%. Okay. So we want to compute that. And here's our z-stat. Our z-stat is negative 0.3. We'll round that. We round that to 3 places. We get negative 0.33, negative 0.300. Okay. So here's our test statistic. And we get our p-value from those results. Here's our p-value, 0.7644. And if we round that to 3 places, we get 0.764. So the key things is pulling out what the alternative is. We always know what the null is, okay, equality there. But be careful about choosing your alternative hypothesis depending upon the language in the problem, all right? So with that, getting those results from StatCrunch, now we can zero in on the conclusions. So the p-value is greater than the significance level, right? So we fail to reject. When the p-value is high, H0 will fly. And there is not sufficient evidence to support the claim, okay? And now we can calculate the 99% confidence interval. Let's go back and do that again. So let's set this up as a confidence interval now. And now compute. And we get our limits of negative 0.0169. Sorry, I'm looking in the wrong box here. Negative 0.165 and 0.131, okay? And here they are. Here are the confidence interval limits here. Those are the correct answers, of course. And we rounded these to 3 places here, okay? Negative 0.165 and 0.131. Okay, now what do we conclude based on the confidence interval? The confidence interval limits include 0. All right, so that conforms with our hypothesis test where we fail to reject, okay? 0 is a possibility, which would support the null that P1 is equal to P2, or that the difference is 0, okay? So by failing to reject, it does not appear to be a significant difference between the 2 proportions. And another way to say that is there is not evidence to support the claim that echinacea treatment has an effect, okay? And so we can also claim that echinacea does not appear to have a significant effect on the infection rate, all right? Questions about 8 or 9? Okay. All right, these are calculations that you've done in the worksheets from chapter 8 and 9. Okay, let's go to number 10 now. How are we doing on time? Ooh, we're running out of time here. Let's keep going until about, at 11:30, we'll do a check to see where we're at, okay? We've got a lot of problems left here, don't we? All right, a group of students estimated the length of 1 minute without reference to a watch or clock. And the times in seconds are listed below. Use a 0.01 significance level to test the claim that these times are from a population with a mean equal to 60 seconds. Does it appear that students are reasonably good at estimating 1 minute? Now, notice that we're not saying that let's test the claim that the students overestimate or that they underestimate. All we're testing is that are there estimates equal to 60 seconds or not? So the correct alternative would be that the mean mu of their estimate in seconds is not equal to 60 seconds, right? That's the alternative. We know that the null is that it's equal to 60 seconds. So the correct answer is D, all right? And now let's determine the correct test statistic here, all right? And in number 10, we're going to use a t-statistic because the sample size is small, but more importantly, we don't know what sigma is, right? We're going to estimate sigma using S. So we're going to use the t. So let's see, let's go ahead and copy and paste this data right into StatCrunch. Okay, so I'm going to do a Command C here. Let's go into StatCrunch now. Let's find an empty column somewhere. Looks like we're going to have to go out to, let's see, I guess we can use variable 18. Let me go back here. All right. And in StatCrunch, we can use let's use variable 18 and now just paste the data right here. And the spreadsheet is a little shifty on us, isn't it? Okay, gotta keep your eyes on it. So here's our data, okay? And in our problem, first thing we'll do is determine a test statistic. Okay. Did you all see how I copied and pasted the data? You see this icon right here? Okay, if we click on that icon, we can copy and paste our data into StatCrunch. All right, so that's a nice shortcut that you can use on your test, on your final. Okay, so let's go back into StatCrunch. And here's our data now, times in seconds of the estimates. And now we'll use a t-test on the mean being equal to 60. So one sample test. We've got the summary. And let's see. Oh, we better calculate the mean and the standard deviation first. Okay, so let's go back to summary stats and calculate our mean and standard deviation here. Okay, and oh wait, we don't need to do that, do we? I'm sorry. Somebody blow the whistle on me here. Okay, we'll use the t with data. Okay, so it's a one sample with data. And here's our data. Okay, and our data is listed in variable 18. So let's select the data in that column. All right, and now we'll do a hypothesis test for the mean equal to 60 against the alternative that it's not equal to 60. Let me again check the significance level was 0.01. So we need to change this to 0.99 to get our 0.01 test. And I think now we're good to go. Okay, we've got our data in variable 18. We've set up our hypothesis test correctly. We've modified our significance level to be 0.999, alpha is 0.01, and now we can calculate our statistics here, and our t-stat is 2.256, rounded to 3 places, with a p-value of 0.0406. Okay. Okay, so let's go back to our test. Input our value, and it says two decimal places. So when we round to 2, we round this to 2, we get 2.26. Okay, and our p-value is 0.0406. Okay, so the correct answer is 2.26, and the p-value is let's check that again. 0.041. If you round 0.0406 to 3, you get 0.041, and that's the correct answer. Okay, 0.041, and then again, looking at 0.041, comparing it to alpha, which is 0.01, we fail to reject because the p-value is high. Okay, so the H0 will fly. All right, so 0.041 is bigger than 0.01. We fail to reject. And then the correct statement would be that there's not sufficient evidence to conclude that the original claim is that the mean of population is 60 seconds. Okay, so the claim is that it's not 60 seconds, and there's not sufficient evidence to support that claim that it's not 60 seconds. Okay, and therefore it appears that as a group, the students are reasonably good at estimating 1 minute. We don't reject the null hypothesis. Okay. All right, let's keep going here. We've got a third of it done. Okay. All right. Now, this problem here is a problem about the power of the test. And we didn't go over the power. We went over the power is the 1 minus the type 2 error. The type 2 error is rejecting, that is accepting the null hypothesis when it's false, okay? 1 minus that probability would be the probability of accepting it when it's true. That's called the power of the test. And so I'm not going to give you this problem on your final, okay? So I will not have a problem on the final involving the power of a test that was put in here by mistake. All right, so let's not even spend time on this problem. You won't get this type of problem on your final. Okay, number 12. Let's see here. Let's read the problem. For conducting a two-tailed hypothesis test with a certain data set, we're not given the data, using the smaller of n1 minus 1 and n2 minus 1 for the degrees of freedom results in df equal to 11, and the corresponding critical values are t equal to plus and minus 2.201. Okay, using the formula for the exact degrees of freedom results in df equal to 19.063, and you saw this in StatCrunch, where StatCrunch gave you sometimes a different value than the minimum of n1 minus 1 and n2 minus 1, okay? And the corresponding critical values are t equal to plus and minus 2.093. Okay, so you get a different set of critical values using a formula that typically we don't use, all right? However, the question involves how is using the critical values of the initial cut at degrees of freedom to be 11. Okay, notice that it's smaller degrees of freedom. Remember, smaller degrees of freedom introduces a larger variance, right? The higher the degrees of freedom, the more peaked your t distribution is. So by using fewer degrees of freedom, we flattened out that curve and gave it more variance. And that'll make it a more conservative test, okay? All right, and that's because these critical values, these are less likely to lead to rejection. Remember, they're farther out in the tails. The farther out in the tails you are, the harder it is to reject. Okay? All right. Any questions about number 12? Okay. All right, let's keep going then. Okay, and let's do this problem here. A study was done on proctored and non-proctored tests. The results are shown in the table. Here's the table over here. So this is our two sample table here. And just take a look at the table there. You can see the results, the two sample sizes, the two sample means, and the two sample standard deviations here. Okay? Comparing proctored versus non-proctored exams. Okay? And so the claim that we're going to test here is that the students taking the non-proctored tests get a higher mean score than those taking the proctored tests. Okay, so now remember, the proctored refer to the first population whose mean is mu sub 1. Okay, that's the mean grade. The population mean is mu sub 1. So the correct set of hypotheses would be that, again, H naught, mu1 is equal to mu2. There's always equality there, versus the alternative that the proctored mean mu1 is less than the non-proctored mean mu2. So the correct answer is C. And we'll use a t-distribution here. So let's go into our t-test. We have time, I think, to finish this one. So we'll go into our t-test here, our two sample t-test. And we've got summaries. Okay, so let's input our statistics here. For proctored, okay, our mean here was 75.86. Our standard deviation is 11.89. And our sample size there is 31. For the non-proctored statistics, we get a mean of 88.41, a standard deviation of 20.46, all right, and the sample size is 32. Okay, all right.
Professor Ruby said she's stuck in the waiting room.
She is. I admitted her already once before. I guess she had to leave.
I think she got kicked out and now she's stuck in the waiting room.
I don't know why or how she would get kicked out, but I hope she's back in now. I don't see her name on our list yet. There she is. Okay. All right. So, okay, are we good to go on this one? Okay. All right. And our hypothesis test is that the two means are equal. And then our alternative would be that mu1 minus mu2 is less than 0. Because we're trying to, the claim is that the proctored test is actually, the mean of the proctored test scores is actually lower than the non-proctored test scores, okay? And our, our significance level here, I believe, was 0.01. Yes. So let's put this, let's specify 99% there. And now compute our hypothesis test. And when we do that, we get a t-stat of about negative 0.2987. Rounded to 3 places, it would be negative 2.988 and a p-value of 0.0022. Okay, all right. And again, I would count the 0.002 as a correct answer. Okay. All right. Okay, and then our p-value here, 0.002, is less than our significance level alpha, which is 0.01. So when the p-value is low, H0 is a no-go, we reject, and the data show sufficient evidence to support the claim that students taking non-proctor tests get a higher mean score than those taking proctor tests, okay? And the confidence intervals, again, I think we have time to do the confidence interval. So let's go back into the confidence interval. And in StatCrunch, remember our, let's see, let's go to our confidence interval now and take the 99%. Remember, it's 99 because it's a one-tailed test. So we have 0.01 area in the left tail. Okay. I'm sorry, that's not correct. This is what we want over here. All right. Wait, let's see. I'm sorry. Okay, here's our data. And now, okay, so there we have our, let's see, our results here for the confidence interval, negative 23.8 and negative 1.303. Okay. Okay, so here we should have negative 23.8 and negative 0.13. So I would count these correct. All right. We've done nothing wrong up here, have we? We've calculated the correct confidence interval there. Okay. So remember that I will be checking your final exams just as I'm going through this practice exam. I'll be doing that with each of your exams, and I'll have a score sheet. I'll have an answer sheet, and I will give you full credit if you conform to my answers. Okay, all right. Because this is how we've learned to do this in StatCrunch using our worksheets. So you've done nothing wrong by coming up with these answers here. All right. Okay, so let's go back to our review. There's the confidence interval. All right. And this interval here does conform with our conclusion based on the hypothesis test, because it only contains, this confidence interval only contains negative values, and which means that it doesn't contain 0. Okay, so if it doesn't contain 0, that means there's some significant effect going on, and we can't support the null that they're the same. Okay, all right, I will end it there. And let's see, what I will do for the rest of this is I will create a video of those solutions. I'll post it today, later today, and then you can look at the video. And remember, we have office hours on Thursday. So if you have any questions about any of the solutions for those problems, we can regather on Thursday at, I believe it's at 11:30. And then we'll take as much time as we need on Thursday to go through those solutions. But you will see a video of those solutions later today. Yes, go ahead.
Professor, is it possible that you could repost this practice final exam so we could try and take it again? Like as practice?
If I have time.
Okay.
I can gin up another test for you.
Okay.
And but also you'll have the video to these solutions as well. Okay.
All right.
All right. But also, hopefully some of you can attend the office hour tomorrow if you have any questions about specific problems, okay? Anything that you see in the solutions that you don't understand, we can go over those tomorrow. That is, I won't have to do a blow-by-blow solution set of the 17 that we haven't done already, okay? So let me get busy and I'll post a video of the solutions to problem 17 through 30, okay? So let me stop the meeting here and I'll post the recording of this much of it immediately, and then I'll create a recording of the solutions of the next 17 problems, okay? And then tomorrow you can connect with the office hour if you have any specific questions. Okay, guys, I'll end the meeting now, and we'll regroup tomorrow. I'm sorry, Thursday. Okay, bye now.